Okay, so we're going to continue with chapter 7. You might finish it today, you might not. There's a lot of examples. Well, we'll see how far we get. So last time we started with the story of statistics, and we mentioned that it's one of the most useful areas of math throughout all facets of life. In fact, if you get a degree in applied mathematics, meaning you study math for the sole purpose of applying it to the real world, what you'll really be studying is probably in statistics, and that will be what you specialize in. And courses that help you study probably in statistics better. Right? So it's a very important and useful tool. It's one of the best tools we have for organizing masses of data. Right? So in everyday life, we're always confronted with all this information, and we need to make decisions on the information, and so we need to somehow organize this to a point that we can make decisions. So we started from scratch. You know, we have all this information given to us, and then we need to organize it. What are we looking at? So one of the most elementary ways was to just throw it in a table, right? Separate your data into categories and count how many data points fall into each category, and we could answer a lot of questions about that. And then we might want to answer even more questions, like percentages, right? So it's not good enough to say, oh, you know, 100 people died from smoking this week, so smoking is bad for you. And it's like, oh, 100 people, that's like really bad. But then if you look, you know, really, 1 million people died this week overall, so smoking is only this percentage, right? So percentage actually gives you a better picture. And so then we'd want to talk about relative frequency, right? What is percentage or proportion of something? You know, and then we'd want to talk about cumulative frequency. How many data points fall up to a certain category and everything below it, right? So we did that with our tables, and we could answer a lot of questions about that. But then we had the situation where the table could get useless, right? Tables can get too big, all these numbers all over the place, people don't like numbers. So then we started drawing pictures, right? And we talked about the pictures we can draw, the ones that are most useful. We talked about bar charts, we talked about histograms, we talked about line graphs. There are tons of other charts, by the way, bar charts and etc., all these stuff. And basically all it is a way to organize the information so that we can just look at it and be able to answer a question. You know, where are most people? You know. But then by studying these pictures, we started to notice patterns, like, oh, sometimes there's a peak. And peaks are important to study because it tells you where most things are. And so you try to study that, and you're trying to say, okay, let's call this value that we have the peak at the central value. And then we want to try to approximate that value, so we developed this thing called the average. And there are many kinds of averages. We spoke about 3 of them. And in different situations, you'd want to use different averages. So then we spoke about averages, trying to get to this central value. And then we want to organize information better than that, because we found that I gave an example where we had 2 totally different data sets, and all the averages coincide. Right? So it means the average wasn't enough to give us a good picture of our data, so we had to go farther. Then we went to how the data is spread out, and we started with the range. And then I gave you another example where it's like you have 2 different data sets with the same range. So it means that the range wasn't enough to get a full picture of our data, so we wanted to go even further. So, and that's where we left off last time. We talked about the range. So from last time, we had that the range was the highest value minus the lowest value. Which is pretty useful some of the time, but we saw that there was an example where we actually had the same range for 2 completely different data sets. And so someone just telling me the range actually isn't enough information. So we had set 1, where was the example? So I gave you 2 sets of grades. Grade set 1, where the class scored these grades. There was a 20, a 66, 45, a 70, a 75, 100, and grade set 2. Where this class, the scores were 20, 90, 95, 95, 98, 100. Now they had the same range. Range was just 100 minus 20, which is just 80. But clearly these are 2 different data sets, and they are quite different. the grade set for the second class is overall much better than the grade set for the first class. These students perform better than those students. However, the range was blind to this fact, right? So that wasn't as useful. So the range only takes into account the lowest number and the highest number, but what really made the difference was in the middle, right? The numbers in the middle weren't lined up. So then we start to think of another way to talk about spread. And so this leads to the idea of interquartile range. I'm going to define what this is in a bit, but the idea is, well, just looking at the endpoints didn't give us enough information, so let's look at the guys inside. Right? So basically the idea is break our data up into 4 parts. And each part is called a quartile. Right? So it's just a range of data points. When you take your data, so you have a bunch of data points here, and you break it into 4 pieces. So this part is the lowest value. This part will be called the first quartile. The middle is the second quartile, which happens to be equal to the median, the exact middle value. This will be the third quartile, and this will be the highest value. So the range only cared about the first and the last, but now I break my data up even more, and I want to look at what's the spread in each of these sections, because you'd realize that number would be different for these 2 data sets, even though the range wasn't different. Right? We want to sort of get to the middle, what's happening in the heart of this data. And so let me just define these guys. So I want to break up the data into pieces because we want to deal with all the pieces on the inside. So let me be specific here. The first quartile is the median of all data points below the median. Second quartile is actually just the median. Third quartile is the median of all data points above the median. Right, so that's the idea. I have this list of data that I've organized in ascending order. I find where the middle is, that's just the median. Then I look at everything below that, right? And I find the median of those data points. The median of that I call the first quartile. Then I look at everything above the median, find the median of that, and that gives me the third quartile. Right? So I've broken this guy up into quartiles, right? This is the first, second, the third. Right? We're actually going to be looking at this. Now we developed what's called the interquartile range, which I mentioned over there. Which we abbreviate IQR, is given by it's the difference between Q3 and Q1. Let's do some examples. With the data set above, for set 1, I want you to tell me what is Q1, what is Q2, what is Q3? For set 2, what is Q1? What is Q2? What is Q3? I also want you to tell me the interquartile range for set 1, and what is the interquartile range for set 2? Okay, using this data set, the one I wrote down over here, these two grids. Let me just rewrite it so you can write it in. Set 1, set 2. Set 1 was 20, 66, 45, 70, 75, 100. Of course, I'd want to arrange this in ascending order, so I'd switch the 66 and the 45. The second grade set was 20, 90, 95, 95, 98, 100. Now notice as far as, yeah.
So when you're like trying to find the median of all the numbers before the median, do you include the number that you're adding to the other number when it's even? And you have to take
Well,
that?
I'm going to look at that. So I'm actually going to do it. And then I'm going to give you a convention. How I expect you to do it all the time, right? So we have these two data sets. Now, as far as the range is concerned, there's no difference between the two. But clearly we can see there's a difference, and we want to be able to know that, right? So we go further and we break it up into pieces, and we want to look at the inter ranges, right? So Q1, let's look at data set 1. Usually the first one, the easiest one to find is going to be Q2, because that's just the median, right? So I have 1, 2, 3, 4, 5, 6 data points. What's the median here? When you start from the outsides, work your way in, you'd realize these two are in the middle. So the median is going to be just the average of these two, right? So it's going to be 66 plus 70 all over 2, which happens to be what? 68. Right? For the second one, you're going to have the same thing. You sort of work your way to the middle. Both 95s are in the middle. So you average those, you just get 95. Okay. Now, how do we get Q1? Well, you see the median sort of happens between these guys. Right? So what you do now is you look below that line, below where the median is. Right?
Okay.
So now we only have 3 numbers to look at. What's the median there? 45, the guy in the middle. Just write down 45. And then, if we were looking at Q3, it means we're looking above this line. What's the median now? 75. So that number is 75. Do the same thing for set 2. So for set 2, the median happened between these guys. So you look at everything below that, there are 3 numbers. What's the median? 90. So you just put 90 here. And you look at the above, median, 98, and put that here. Now when you look at these, you can start to see differences, right? The range had no difference, but clearly you can see here, in the first quartile, one class got up to 90, the other one only got up to 45, right? By the time you're in the third quartile, this guy's up to 98, that's only at 75. Clearly the data points in the second one had higher values, even though the range was the same. So we can start to see the difference between our 2 data sets here, right? Before the range, we couldn't see any difference. What is the interquartile range for the first set?
30.
30. You just take Q3 minus Q1. So like in the middle of this data set, the range was 30. Right? What is the interquartile range for the second one?
80.
Right, you take Q3 minus Q1. That's just 8. So that sort of tells you, yeah, the first and last values were exactly the same, but the second one has the data a lot more spread out. Well, the first one has the data a lot more spread out. You can go through a distance of 30 between the first quartile and the second quartile. While the grades in the second set were really close together, you only managed a distance of 8. So you can see that from the data point. A lot of people got into the 90s. It's really clustered together. While here, you could rate from a 45 all the way to a 75. So the spread of this one is in some sense larger, even though overall the spread isn't. So we're sort of starting to see a difference between these data sets now. And talking about quartiles leads us to another kind of graph, which is a very famous kind of graph. It's called the box plot, aka the whisker plot. And this one is basically a graph of the quartiles. So let me just draw the one for the first set to show you. Every good chart has a title, box plot for grade set 1. So here's how it looks. You sort of draw it on a number line. So let's say we're going from 0 to 100. So basically you put in all the important numbers, the lowest value, the highest value, and all the quartiles. Right? So our lowest value was 20, right? This is the lowest value. The highest value was actually 100. And then you're going to put in all the quartiles. So this is for data set 1. So let's look at data set 1. Our Q1 was actually 45, so almost halfway. 45, that's Q1. Our Q2 was at 68, so a little more than halfway, 68. Our Q3 was 75. So this is Q2, this is Q3. And here's how the diagram looks. You draw a box that goes from the interquartile range. The guy that here cuts through the median, you draw a line through the box. Then what you do is you draw a line, straight line here. That's called the whisker. That's why it might be called the whisker plot. And then you have a straight line. This is called a box plot. It's not a part of our consideration here, but I would just mention the middle of the box. If you look at the box and try to find the exact middle, that is theoretically where the mean will happen. Sometimes they ask you a question, how does the median relate to the mean? And if you have a box plot, you can sort of tell. So in this case, the median was higher than the mean average. But if you want to draw a box plot, you only need the quartiles. So you find the lowest value, the highest value, and all the quartiles. And that is defined to be the box plot. I don't know if there's still too much glimmer here. Let me close this up. Are we okay so far? Any questions so far? So, why I'm really doing it this way is I just want you guys to appreciate that statistics, they don't just throw all these things just to annoy you. There are reasons. Like every time we hit a roadblock, we have to invent something to get beyond it, right? So you thought of the average and the range, but we realized there are times when we don't have enough information. So we have to invent something else to get more information. Right? Eventually, the amount of things we invent stops because for all practical purposes, we have enough information that we'll ever need, but so far we have to keep building on things. And we want to get to a nice, happy median. So that's the idea. Sometimes the range doesn't give us enough information, so we start to look at interquartile ranges. How does the data in the middle behave? Because a lot of times that tells us a difference that just the range doesn't. What does the box plot for grade set 2 look like? Take some time and draw that. It shouldn't be too difficult. There's a third. So quartile should have been labeled 2. We started with 1, which was the range, but it wasn't good enough, so we invented quartiles. Now we're talking about the third measure of variation, which is called the standard deviation. By the way, question. What do you think it means, pardon the pun, what do you think it means for the mean to be lower than the median? How do you describe what that means? There's a lot of variance.
There's a low outlier. So the mean is lower than the median. Right?
There's a low outlier. It doesn't necessarily have to be an outlier.
There's one.
But you can think of most data points happen to be below the median, right? So in this particular case, the mass of people got grades that are below the median in some sense, right? So that's how you can sort of think of it. The mean is going to be where the cluster of people are. But the guy in the middle is actually performing above that, right? That's one way to think about it. Okay, what does the one for data set 2 look like?
All the way up.
So again, we do this 0 to 100. What's the first number you have on this?
90.
90 is the second number, right?
Q1.
So that's all the way close to the end. That's 90. What's the third number? 95.
98.
The 95 and then 98. So for this one, the box is all the way over here. The 95 should sort of be closer to the 98. So now this indicates that there's a real outlier. There's this one kid that's pulling down the average of the class, right? That's what it sort of looks like, right? So clearly the range, these guys look very different, but when you started considering quartiles and then you started graphing it, you sort of realize the data points are actually pretty different here, right? Most people are performing better in this class, but then you have this like one kid or these few these two students that are pulling down everyone down, right? Whereas this one, it's more spread out. Everyone is sort of performing at the same level, kind of, sort of, but the masses of them are falling here. So we can sort of tell the difference between our data that we couldn't really tell before, given just the range. So now we are going to talk about the standard deviation. This one shows up all the time, and I'm going to probably talk about why we use it so often later. Because it gives us a lot of predictive power, this one. And it's probably the most famous measure of variation. We sort of, based on it's not based on quartiles, it's based on the mean average distance between the data points. And the mean. So we sort of think of trying to measure the average distance that points deviate from what the mean average is. And like I said, the mean average is a very common average to take. A lot of things in life follow, it makes sense to take a mean average of. This idea of a sample is going to be, we're going to talk about that later. A sample is just, right? You call the population all the data that you have, but a sample is just a select few that you want to do your research on. And we're going to talk about why being able to choose the right sample is important. But for now, just we're going to define the standard deviation for the sample, the guy that we're actually studying. A sample with n elements, the standard deviation of a sample with n elements is given by, here's the form. The notation is S, lowercase s. This is standard deviation for a sample. There's a standard deviation of a population that uses a different letter, but we use S to do the one for the sample. This is the formula. So we're measuring using the distance form to measure the distance between each data point and the mean distance. There are n data points, so I do this n times the square root of that, and I divide by n minus 1. Right? So it's not exactly the average, that's because it's only a sample. I'll probably talk about that later. What?
The x with the line.
Where x bar equals the mean of the data set. x1 to xn are the data points. There are n of them. Little s is the standard deviation. N is the number, well, I already mentioned that, number of data points in the sample. So we sort of average the distance between each data point. And it sort of comes from the distance formula. It'll probably be more clear if you plot it on a graph, but I don't really care about deriving that formula for now. Just that's where it comes from. Let's actually talk about it. Let's actually do an example. I'm going to use the same list of grades I had before. 20, 45, 66, 70, 75, 20, 95, 8, 100. I'm going to attack this in two different ways. It's just two different ways to write it out. So part A. So this is the formula for standard deviation, which means I'm going to need to know the mean, right, in order to apply this formula. So the first thing I have to know is what the mean is. What's the mean of this data set?
64.
So it's going to be 20 plus 45 plus 66 plus 70 plus 75 plus 100 over, there were 6. That's actually 64?
62.6.
Yes, I computed it before, 62.67. Okay, so now that I know that, the standard deviation is S is going to be equal to we're going to do this. So I'm going to take the first, so these are my data points, x1, x2, x3, x4, x5, x6. So n is 6 in this case. So I'm going to take each of these, subtract that, and square it. So 20 minus 62.67 squared plus 45 minus 62.67 squared plus 66 minus 62.67 squared plus 70 minus 62.67 squared plus 75 minus 62.67 squared plus 100 minus 62.67 squared. All of that over 6 minus 1. And take the square root. And you plug that into your calculator. And you should get, I actually did this at home, 27.36. Rounded to 2 decimal places. Any questions? Just so you know, your calculator might actually have a function that will compute the standard deviation for you. But I would at least expect you to just write this formula down Right? If you don't want to plug it into your calculator, you can use a built-in function. Most calculators have that now. So you just write this down and then tell me what the answer is. But that's the idea. We're just using that formula. That you're going to need to memorize. We don't give you formula sheets. Yeah?
Can you use another formula from a different class? Or do you have to do that?
What other formula is it?
You want to write it down? It's like the summation of x squared minus summation of the x squared over n minus 1. The square root of that.
It's actually the same thing.
Yeah, no. This one's more different. So they do it as a negative.
It's pretty much the same thing. The summation is just a way of saying add these things over and over. So, I mean, if you write that down, it's just a condensed form of writing this. It's basically the same form. So, if you write it that way, I don't really care. It's really the same thing, just written in different notation. They try to write it in more compact notation. But it's basically the same thing. In the background, this is what's happening. Anyway, so that's that. Now, typically, how people do this is they try to throw things in a table. So let me do that in part B. So in part B, again, we need the mean, which is x bar, which is 20 plus 90 plus 95 plus 95 plus 98 plus 100 all over 6. And we got here to be 83. So now it's actually, people like to set this up in a table. They just do the formulas. So we have the data points here, which we call xi. That's to represent x1, 2, 3, blah, blah, blah. So here we had 20, 90, 95, 95, 98, 100. And the next column, they take xi minus x bar, and so they're computing each one of these guys. So here you'll take 20 minus that 62.67.
83.
No, 83.
83. Right? Which in this case is what? Negative what?
62.
Negative 63. Here you would take 90 minus 83,
7.
which is just 7. Here you would take 95 minus 83, 12. Here you would take, again, 95 minus 83, which is again
12.
Which is again 12.
It's 13.
Did math change between these two? We add them differently now since the last time. Yeah.
Universe.
Okay. 98 minus 83.
Accelerated particle.
Yeah.
Accelerator.
Shit, the
Yeah, those damn physicists broke something in that particle accelerator.
The Geneva people.
98 minus 83.
15.
15. And then we do 100 minus 83.
17.
And then we have 17. And then we do the next step in the formula, which is to square everybody. So in a lot of textbooks, you'll see this table. This is where they're getting it from. They're just breaking down that big formula into nice, manageable chunks. So basically, they're going to square this. Minus 63 squared, 7 squared, 12 squared, 12 squared, 15 squared, 17 squared. And they're going to get numbers. 49, this is 134, 134. 15 squared, I should know what that is, but I forgot at the moment. What's 63 squared? 3969. And 15, like 225. 17? Huh?
289.
289, right? Now the next thing you're going to do is you're going to have to add all these guys together. So here you sort of do the total. So you add all these numbers together, and what do you get? 4,820. So this is like the sum of your xi minus x bar squared, which in some formulas you might see that. That's uppercase sigma. It just means add all these guys together, basically. And so that is all we need. This means our standard deviation is just the square root of this number, 4820 over 6 minus 1. Which is, I computed that, 31.05. So some people like to use tables to organize everything, so that's how you do it in that case. Any questions on this so far? So this is just another way to describe the spread by describing the average distance between all the data points and the mean average. Right? So it's just a formula you have to know and apply, or at least know where it comes from. There's another thing called the variance. Right? Now remember, variance is just a number to describe the thread. This, by definition, is defined as the square of the standard deviation. Obviously invented by someone who couldn't bother to take the square root. So let's just look at that number. I'm done computing. Okay, so I give you the notation. Yes.
Yeah.
That is variance is equal to s squared. That's something you need to know. Just in case you're asked about it, right? It just means the square of the standard deviation. Basically, get rid of the square root because it's ugly. If you ever need the standard deviation, you just take the square root of the variance. It will give you the same thing. So, example, for set 1 of variance, your x squared, would just be equal to the standard deviation squared, which was 27.36 squared, which was 748.67. And for set 2, variance was equal to our standard deviation squared, which was 31.05 squared, which is going to be 964. Let's talk about shape. So I know some of you are like, well, I was happy with the whole box plot thing in quartiles. just break it up into 4 pieces and use those numbers. Why go through the trouble of inventing this complicated formula, right? Well, it all actually goes back to shape, is the reason why we'd want to even do this in the first place. It turns out that a very typical is the symmetric bell curve. It just so turns out that a lot of the things we want to study, when we try to graph them and try to describe the shape of the graph, this is the shape we'll end up with. Especially for those of you with doctors, anything has to do with human beings, normally if you plot it, take statistics on it and plot the graph, the graph will have this shape. Which means it's symmetric, which means the best average to use would be the mean. Remember, we spoke about this last time. The mean is the best average to use if everything sort of comes towards the center, right? You use the median if you have like these huge outliers, right? And you use like mode if there's like a lot of people just concentrating on one point and everyone else is sort of just spread out evenly throughout everywhere else, right? So the fact that a lot of the things we study have this shape, the mean turns out to be the best average. So then I wouldn't really want to use quartiles because the average that the quartiles use is the median. It was developed based on the median average. I need some way to describe spread using the mean average, and that's what the standard deviation is, right? And it turns out that when I use that average and the spread, if I talk about the mean and the standard deviation, I actually know a lot of information about a typical data set. It turns out it's highly predictable. These things are highly predictable. Turns out we know a lot about this shape. Mathematicians have even figured out the formula that gives you that shape. It's that we know that much about it, right? We know a lot about this shape. Right? And I'm going to tell you some of the things we know. We'll say more when we get to normal distributions, but for now I'm going to tell you some of the stuff we know. But for now, here's one thing we know. Called the normal distribution. I'm not sure why it's called the normal distribution, but maybe it's because it's the normal thing to happen. I think it's very usual. One thing we know is the bell curve rule. Or it's sometimes called the 68, 95, 99.7 rule. This is a rule we know. And basically the rule says the following. This is the rule here. So this is where the numbers come from. 68% of the data points are within one standard deviation from next number in the rule is the 95. 95% of the data points are within 2 standard deviations of the mean. And 99.7% of data points are within 3 standard deviations of the mean. So I can actually tell about the percentages that occur in this data set. So if I have a bell curve, the mean is going to be where everyone's clustering around. That's the mean, that's x bar. Now if I add the standard deviation, go to x bar plus the standard deviation, and I subtract the standard deviation, x bar minus the standard deviation, then within that range, there's 68% of the data points. If I go further, like within an interval of 2 standard deviations, to x bar minus 2 standard deviations, within that range, 95% of my data points will fall. If I go further, 3 standard deviations length interval, x bar plus 3 standard deviations. Then 99.7% of all my data points will be within that range. This is called the 68, 95, 99.7 rule. And it happens for bell curves. Any bell curve will have this happening. Sort of a rule. Furthermore, we can approximate the standard deviation from the range. So finding standard deviation is annoying. It turns out with this shaped data, we can actually approximate standard deviations using the thing that's easy to find, which is the range. This is called the range rule. And it's just S is approximately equal to the range divided by 4. So, just to recap on what we've discovered so far. Right, so we have to organize all this data. We threw it in tables. Tables got too cumbersome. We made graphs. We're looking at graphs. You notice patterns. Then we try to get to this whole typical value thing. So we talk about averages. Averages wasn't enough because I can have 2 different data sets with the same average, but they're very different. So then I started to talk about spread. One of the most elementary measurements of that was range, the difference between the lowest and the highest values. But then we realized 2 very different data sets can have the same one of that too. So then we started talking about quartiles, breaking it up, looking at the middle part as well. And that was based on the median, which it turns out most of the things we study, that is not a good average to use. The mean is the best average to use by far for most typical things we will study. So then we figured out a way to determine spread in terms of the mean, which is the standard deviation. And it turns out that a lot of data sets that use this happen to have this shape, and this shape we know tons about. I can tell you how many people will fall in certain ranges, right? Down to the percentage, right? And I can also, with this shape data, get an approximation for the standard deviation, which is really cumbersome to calculate, by using the range over 4. And once I know I have this shape data, I know all of this automatically. I can just assume that all this is true. Right? So that's why it's very powerful just knowing this. And it turns out a lot of things fall into this category. Right, so did I have an example of estimating the range? No, I didn't do that. Okay. We're going to move on to estimation. This is a very important topic. You more than likely you'll have to be able to do this on the final, so I'm going to talk about that. At this point, though, I'd just like to mention that we've sort of hit a sweet spot in statistics. Right? Remember, we were at the point where we had to keep developing new things to answer more questions. Right here, we're actually in a pretty sweet spot. We can answer a lot of questions. If you give me a data set, you know it follows the mean is the best average. All you have to do is tell me what the mean is and what the standard deviation is, and I can pretty much answer any question I want to answer. Right? There's no need to develop anything anymore. Right? So we've sort of gotten to this point where, hey, I can tell a lot just with these small pieces of information, and I also know information of how to approximate the important things that I need. Right? So it's a really nice place to be, and we're just going to be chilling here and sort of applying what we know for now, because knowing this tells us a lot. We can distinguish between different data sets very easily using what we have so far. So we don't really have to go further and invent something new, think, what if the standard deviation isn't enough? It turns out it is. Right? We'll never really need something anymore to answer most of our questions. And I'm going to sort of show you how this all applies. Let's hope we can get a couple good examples in. Let's go back to the example with 20 grades. I gave you this list before. We did this last time. Okay, so I gave you that list of 20 grades, and we already actually put it in a table. So we had grades 50 to 60, 60 to 70, 70 to 80, 80 to 90, 90 to 100, the total. So we threw this in a table, 3, 6, 5, 4. There were 2 grades here for a total of 20 grades. The percentage here was 15, 30%, 25%, 20%, 10%, which adds up to 1. Right? So remember, before I wrote out this whole list of grades, right? It wasn't very useful, so I decided to throw it in a table and just count the frequency in a certain range. Now the question is, I want to be able to analyze this and answer questions about it, right? Now I know the best way to do this is to find the mean and the standard deviation. But obviously I lost some information by putting it in this table. I don't know what the exact grades are anymore, right? I just know 3 of them are somewhere in this range, 6 of them are somewhere in this range. I don't know the exact grades anymore, right? So I put my information in a short table that's more usable to me, but now I'm worried, did I lose all the information I need to actually answer some important questions? The idea is no, we can actually estimate all the important things we need from this table. Right? And that's going to be an important thing to do in the final, actually. For example, you will be given a table like this, and they're going to ask you, find the mean, find the standard deviation, right? You don't actually know all the data points, but we will be able to get an estimate for them, and often the estimates will be pretty good. I'm going to actually estimate the things here, so you can actually see it in action. So one thing you realize from this, computing the mean and the standard deviation, they're sort of annoying things to do, right? So you don't want to like add all 20 grades and then divide by 20, and then you don't want to take the square root of the difference of all those and then throw them in here. So what you can do, put them in a table, it's more manageable. Now let's see if we can actually get back to those guys. Let's start with the mean. We want to find the mean, the median, the standard deviation. Okay, let's start with the mean. The trick here, that's the first trick we're going to use. Basically, I'm going to pretend that every value in the 50 to 60 range takes on the mean value in that range, right? So what is the average of 50 and 60? 55. So pretty much I'm going to pretend, you know what? I'm going to pretend all the grades in that were 55, right? Everyone who ends up between 50 and 60, assume their grade is 55. Right? So this would imply that our mean is, we have to add up all these grades, right? So I'm going to add 3 55s, right? Plus 6 65s, right? This is the mean of 50 and 60. Hopefully you can see that. In the next bin, what's the average number? 75. How many of those I have? I have 5 75s. I have 4 85s. I have 2 95s. All of that over the total, which I now know is 20. I computed this before. So this actually gave us an integer. This is exactly 73. Now, by the way, I went through and I did the mean the hard way, added all 20 numbers and divided by 20. And the actual mean was 71.95. So the actual mean is about 72, and using this approximation, I got 73. Pretty close, right? And notice I don't know what all the grades are, but I can still get pretty close to what the average is, right? So that's an important thing to be able to do. Makes your computational life easier, and it allows you to get a lot of information out of a summary of your information. Any questions on this so far? Like I said, it's an important topic. So if there's anything that's not clear. Yeah. Oh, I said, I'm explaining what the 55 is. It's the mean of 50 and 60. Right, so you look at the interval, it goes from 50 to 60. The average of those two is right in the middle, 55. I'm going to pretend that all numbers in that interval is that value, 55. Right? So now I'm sort of taking an average of averages. And it turns out that's actually close to the real average. So doing this estimate, right? Doing this was a lot easier than adding 20 numbers and dividing by 20, right? And so I could actually get something pretty close to the actual answer, right? Not exactly, but it's an estimate. We're estimating, right? Sometimes an estimate is all we need. And it's around 73 people, you know, give or take. Next, let me do the standard deviation next. Again, assume all values take on the mean value in their interval. So again, for example, I know there are 3 grades in the range 50 to 60. Pretend they're all 55s. Right? And there are 6 grades between 60 and 70. Pretend they're all 65s. There are 5 grades between 70 and 80. Pretend they're all 75s. Right? Just estimating. Pretend they all take on the value of the average value of the interval. Right? And so now I can compute my standard deviation using that formula. But now the thing is, I don't have to do the formula with 20 terms in it. I can actually cut it down. I know there are 3 terms where I'm going to use the estimate of 55 minus the mean, 73. There are 6 terms where I'm going to assume they're 65 minus the mean. There are 5 terms where I'm going to assume they're all 75. There are 4 terms where I'm going to assume they're all 85s. There are 2 numbers where I'm going to assume they're all 95s. So instead of adding 20 numbers, I'm adding 1, 2, 3, 4, 5 numbers. And that's all over 20 minus 1. So this is approximately, I did the computations earlier. I got 12.39694. By the way, FYI, I did it the long way and I got S actual value. It's actually 12.28381. You see, again, our approximation is like super close. And this is only with 20 values. I mean, imagine if my data set had 1,000 values, it would actually be closer. You really need more space here. Hopefully you have this table. I'm going to get rid of it because I'm going to need the space, I think. For the median, we're going to change our strategy a little bit. We're going to use linear interpolation. Sounds fancy. Basically means that we're assuming all the points in the interval fall on a straight line and they're evenly spaced. So we're estimating, so we're assuming ideal conditions prevail, right? So I want to find the median number. I'm just going to assume in each category they're evenly spaced out, so I can just count them up. Yeah.
So all of these methods get less accurate when the interval is bigger. Like say it was like 50 to.
They get more accurate with bigger intervals, especially if you have more data points. It depends on the density of your data points. If you have a lot of data points packed into like an interval of 10, then it'll be super close.
So if you gets more accurate, the higher the bins you have.
The more data points
Not,
we have.
well, I'll be fine, but like, wouldn't it make more sense that if we had a smaller bins as opposed to like having 10 values in the range, we had like 5. So if we went like from 55 to 50 or whatever, 50 to 55 as opposed to 50 to 60. You see what I'm saying? If we broke up the numbers that way, would it be more accurate then?
Well, what you look at is relative density. Like how much would be packed into half the interval as opposed to the whole interval.
So if it's worth it,
If it's worth it, you would go bigger. Very usually, though, they'll tell you how they want you to set up the bins. So it's not a call you'd have to make. But if you're actually doing the research yourself, it might be a call you'd have to make. You probably want to choose your bins so that, you know, it makes your work easier, but at the same time, you make them as dense as possible. So you have a lot of numbers, and so the increments that your error could be off by are smaller. So let's begin. Remember, the median is the number in the middle, right? This all sounds really complicated, but it's easier than it is, so let me just explain. We have 20 data points. So the median is around the 20 divided by 2 position equals the 10th position. Now technically I know it's an even number of data points, really should be the average of the 10th and the 11th position, but it's an estimate, right? Just divide it by 2, that's the position we're after. Right? So we basically want to figure out what's the 10th number, right? That's sort of what we want to approximate. What is the 10th number of this data set? Maybe I should redraw the table. It's going to be easier to explain if you actually see the table. I want to figure out the 10th number. So the table is grade, frequency. Relative frequency is actually not important for us here, but grade and frequency, so I have 50 to 60, 60 to 70, 70 to 80, 80 to 90, 90 to 100. So we have 3, we have 6, we have 5, we have 4, we have 2. Okay. So now we're pretty much counting them off. The cumulative frequency is actually more important here. Right, so you start by counting, right? You have 3 guys here. You move down to this bin, how many guys do you have now? You have 9, which means you have to keep going further, right? So the 10th number is one number into this bin. Right? By going through the first 2 bins, we only get 9. Means I need to take 1 more right? So my median is going to fall somewhere between 70 and 80. Now I'm going to want to approximate what that number is. Right? The 10th number. And it's going to be easier than you think because I'm assuming they're all evenly spaced out. Right? So I have 5 numbers between 70 and 80. If they were evenly spaced out, like how far apart would they be, right?
So it has to be.
So I'm going to again call this the step size. We also used that for our delta x previously, but here I'm going to call it the step size. Here, since we're assuming evenly spaced, the step size would be what? That's the distance between each number. It's going to be the bin length divided by the frequency. Right? I know there's a distance of 10 total between this whole interval, but I want to divide it up into each, how many numbers there are. That's going to tell me the distance between each number. Do I have that here? So note, bin length is just the range of the bin. So in this case, here we have that step size is equal to the bin length, which is just going to be 80 minus 70 all over. There are 5 numbers in this bin. Right? So they range over a length of 10, but there are really only 5 of these numbers. That means the step size is 2. Right? If I have 5 numbers covering an interval of 10, they should be 2 units apart. Right? You can sort of figure that out intuitively, but it's nice having a formula that tells you this as well. So all my numbers are, yeah.
Since it's open-ended, wouldn't it be 80 minus 71?
That's sort of, it's an approximation.
Okay.
You sort of think of this interval as having length 10. So the step size is 2, which means you're expecting the numbers to be spaced out in this way. Like, if there are 5 numbers, you should have like a 72, a 74, a 76, a 78, and an 80. That gives you the 5 numbers. They're all 2 apart, right? So those are your numbers. So the median, so if you think of this, the median then, did I write on the formula for this? You can think of it as the left endpoint plus the number of steps you need to take, which tells you how many numbers you need to go in. Times the step size, right? So you're taking several steps of this size. So again, it's good to, again, it's sort of something you could, if you take a while to think about it, come up with common sense for this, but it's nice to have a formula where you know you're in an exam, you don't have to think about it, just know, okay, this is how we do it. So these are 2 good formulas to have. So in this case, what is it going to be? Well, the left endpoint is 70 plus, how many numbers into the bin do I have to go? Only one number into the bin, because I need to get to the 10th number, and I've covered 9 before this bin, so I only need to go one more. How far into the bin do I need to go? Well, by the step size. That is 2. So the median here should be about 72. Actual median, if you look at the actual data set, I think I did that, it's actually 71. So again, not bad of an approximation. Let's end with another example. Grade, frequency. So these are more grades. 40 to 50, 50 to 60, 60 to 70, 70 to 80, 80 to 90, 90 to 100. You may or may not be given the total, but here I'll just tell you, it's actually 32 grades. There are 32 students in this class. And here's the grade breakdown for the tester or whatever. There are 3 students that scored in that range, 3 scored in that range, 8, 11, 4, and we have 3 students getting above a 90. Probably won't have time to do the standard deviation, but you could also do. You can also do the standard deviation. Maybe do that at home for practice. But this is actually a typical problem that you could be asked. Right? In the final, they'll give you this table. It'll be described in terms of bin data, so you don't actually know what the actual data points are, but they're going to want you to be able to estimate these values based on this table. Right? So let us begin. What is the mean? There are 3 numbers in here. Assume they all take on what value?
45.
45, the average, right? So this is just going to be 3 times 45 plus 3 times 55 plus 8 times 65 plus 11 times 75 plus 4 times 85 plus 3 times 95, and all that over 32. Did I actually do this one? No, I didn't. So, when someone gets that, they can tell me. Median.
70.93.
70.93 is our approximation here. The average grade in this class, the mean average grade is around a 70. So on average, the class is pulling a C off it. The median here is, we have 32 numbers, which means the median is roughly the 32 over 2 the 16th number. Right? Now how do we get to the 16th number? Well, we start adding them up until we hit 16, try to figure out where we are, right? So here I start out with 3, here I'd have 6, I add 6 plus 8, I get 14, right? Which means the 16th number ends up here, 2 numbers in. That's the number of steps. So here I'm going to figure out the step size. That's just going to equal to the length of the bin, which is 80 minus 70, all over. How many people are in this bin? 11. So that's going to be what? 10 divided by 11? Huh? 0.90 or 0.91, let's keep it like that. So this means that the median is the left number plus number of steps times step size. Number of steps is how many numbers into the bin we need. We need 2 more numbers, because up to just before that bin we had 14, which means we need 2 numbers into this bin. So the left endpoint is 70, plus we need 2 numbers, and we're walking at a size of 0.91. And that gives us 71.82 will be our approximation for the median. 70.93 is our approximation for the mean. And time's up. We will stop there. We actually covered all I wanted to cover from chapter 7, so you can try the homework for that next time.